Welcome back, everybody. In this video, we're continuing with section 5.1 with some more examples. So the example we've got here involves a public speaker, and the speaker computes probabilities for the number of speeches she gives each week. And so we have the possible outcomes and the probabilities, corresponding probabilities shown in the table. What we're to do is find the mean, variance, and standard deviation of this distribution. So mostly a pretty routine application of these couple of formulas from section 5.1. So let's begin by finding the mean. So for the mean, we need to find the sum of the xp of x's. So let's begin with that. Mu will be the sum of xp of x. And so we'll have each outcome times each probability. So that's 0 times 0.06 plus 1 times 0.42. And then we're going to do that for all of those, all the way down to 5 times 0.03. Okay, so let's see. All right, so I got 1.87 for that. Of course, we're going to round this here in a minute. Because our possible values for x are integers. So based on the round off rule, we should give our results to the nearest tenth. So I'll round this to 1.9, but I'll hold off on rounding until later. So for the variance, we'll take each x value squared times each probability, add all those up, and then subtract the mean squared. So let's get the variance. So for the variance, we take each x squared times the corresponding probability. And this takes a little time. Okay, so there's each x squared times the corresponding probability. And then we will subtract 1.87 squared from that. Okay, so once more calculate. All right, so going through all the calculations, this is what we get. So for the mean, we add 1.87, and then we're going to round that to 1.9. Okay, for the variance, it ended up being about 2.03. We're going to round that to the nearest tenth, getting 2.0. And then the standard deviation, we're going to take the square root of our 2.033, and that rounds to about 1.4. All right, so there's our mean and standard deviation and variance. So one of the main things that we find out this information for is so that we can decide what we would consider values of our variable that are unusual or unusually high or unusually low or significantly high or significantly low. In some sense. And so that's what we're going to end up working on very soon. Before we do that, though, I want to do one more expected value problem. So the other problems that we've done involving expected value have dealt more with games like rolling dice or spinning a spinner. This one has to do with an insurance company. So the story goes like this. It says an insurance company is determined that they won't need to pay a claim for 99.4% of its clients. There's a 0.4% chance they'll need to pay out $30,000, a 0.1% chance of paying $60,000, and a 0.1% chance that they'll pay $90,000. So based on that, we want to know how the insurance company should set their premium so that they could cover the cost of their claims. So that's the way insurance works, right? Is that most of the time you don't need the insurance, and so it can seem like you're paying for your insurance for no reason, but then when you do need your insurance, you need it. And so that's how it works. But the thing is they've set the premium to cover the cost of what they end up paying out. And then, of course, there's money left over for profits and cost of doing business and all that. So we want to figure out, just taking the information shown here into account, how should they set their premium? So we're going to, again, write down a table showing basically the different outcomes and the different probabilities. So we'll have an outcome and a probability, and we're going to find the expectation. So the first outcome is 0, basically. They're not going to pay a claim. for 99.4% of their clients. So I'm going to write that as a decimal at 0.994. And then there's a 0.4% chance that they'll need to pay $30,000. So 0.4% chance is 0.004. And for that, they're going to need to pay $30,000. I'm going to write that as a negative value to represent the fact that they're paying it. And then a 10% or a tenth of a percent chance that they'll need to pay out $60,000. And then finally, a tenth of a percent chance that they'll need to pay out $90,000. So when they pay out, they're going to have to pay out a lot, right? But 99.4% of the time, they don't have to pay out anything. So we need to rig it so that the other 99.4% of the time covers basically the cost of those payouts. All right, so our expectation is going to be the sum of the xp of x's. So we'll multiply each x by each p of x and add the results. So that's 0 times 0.994 plus negative 30,000 times 0.004. And then let's just go ahead and put the others down here. Negative 60,000 times 0.001. And then negative 90,000 times 0.001. Okay, and so then let's see what we get. All right, so what we get is negative 270. So how to interpret that? Basically, we know that 99.4% of the time the insurance company won't pay out anything. But then there's these very small chances that they'll end up paying out these large amounts. So on average, it's going to be as if they paid out $270 to everybody, right? That's the long run average. And so to offset that, we should charge $270. That would be how they should set their premium to cover basically these payouts. Okay, so now moving on, one of the things we want to be able to do is decide whether an outcome of some random process is significantly high or significantly low. And we have two ways of doing that. One is in terms of the standard deviation, and one is in terms of probabilities. So let's take a look at both. The first one has to do with the range rule of thumb, and it says that significantly low values are basically 2 standard deviations below the mean or lower, and significantly high values are 2 standard deviations above the mean or higher, okay? And values that are just run-of-the-mill, not significant, are the ones that are between, right? Between mean minus 2 sigmas and mean plus 2 sigmas. So the graphic here really illustrates that. We've got a mean, right? The sum of the xp of x's in this case. And if you go down by 2 standard deviations or up by 2 standard deviations, we're going to count those values as not being significant. But if we get lower than 2 standard deviations below the mean or higher than 2 standard deviations above the mean, we're going to call that significant. Okay, so let's see an example. So the table that is shown here shows groups of 8 births from 8 different sets of parents, okay? And this measures the number of girls in those 8 births. So kind of like the example we'd had earlier with groups of 6 people sitting at a table. This is groups of 8 sets of parents, and so there's 8 babies. Within those 8 babies, how many girls? So there's a 0.004 chance that out of those 8 babies, you'll have no girls, and a 0.109 chance that out of those 8 babies, you'll have 6 girls. So that's how to read the table. Out of 8 babies, the number of girls is basically how to read the table. And then what is the probability of getting that number of girls in 8 babies? Okay, so the first thing to do is to find the mean number of girls here. So the mean is going to be the sum of xp of x. And so for this, that is 0 times 0.004 plus 1 times 0.031, and then all the way down to the end, we'll have 8 times 0.004. Okay, so let me go ahead and calculate that. All right, so going through the calculations, we get 3.996, or when you round it, you're going to get 4 girls. So that shouldn't be too surprising, right? Out of 8 kids to get 4 babies, that makes 4 girl babies, that makes sense. So basically we'll say that's going to round to 4. Okay, so then next thing we want to do is to get the standard deviation of the number of girls. So for your convenience, I've got the formula located to the right. So once again, we'll take x squared times p of x, and we'll subtract from it our squared mean, and then at the very end, we're going to take a square root to get the standard deviation. Okay, so we need the sum of x squared p of x minus mu squared. I'm going to figure that out, and I'll do the square root in a separate step. Okay, so each x squared times a p of x. So 0 squared times 0.004, and then 1 squared times 0.031, and 2 squared times 0.109, and then we'll go all the way down to 8 squared times 0.004. And then at the end, we'll have in the back minus the mean squared. And here I'm going to use the non-rounded version, the 3.996 squared. Okay, so let's go ahead and get that next. All right, so finishing up the calculations, which does take a little while, we ended up with a mean of 4 and then a standard deviation of about 1.4, of course, assuming that we've done some rounding. Okay, so now let's see how we can use that criterion to determine what we'd consider significantly high or significantly low. Okay, so this slide shows basically a repeat of what we just saw. We're to use the range rule of thumb to determine if 1 is a significantly low number of girls or not. So to do that, we would want to know, is it more than 2 standard deviations below the mean? So the mean minus 2 standard deviations, that's 4 minus 2 times 1.4. Okay, so this gives us 4 minus 2.8. Okay, is 1.2. Okay, so 2 standard deviations below the mean would be 1.2 girls out of 8. So 1 is significantly low because it's more than 2 standard deviations below the mean. Okay, next we want to decide if 6 is significantly high. So we want to know that's mean plus 2 standard deviations. The mean was 4 plus 2 times 1.4. That's 6.8, right? Okay, and that's bigger than 6. Okay, so that's not significantly high. Okay. All right, so that's how the criterion works, basically, is you have a probability distribution. You can go through the formulas to decide on the mean and standard deviation. And then any values of the variable that are within 2 standard deviations of the mean are not considered significantly high or low. And if they're outside, then they're significantly high or low. That is the first way of considering the significantly high or significantly low. The second way is in terms of probabilities. And so that reads like this. So there's 2 paragraphs from our book that are important for this, and they're phrased really similarly. So you want to read through them really carefully. Let's take a look. So first of all, for a significantly high number of successes, X successes among N trials is significantly high if the probability of X or more is 0.5 or less. Okay, that is, X is a significantly high number of successes if the probability of X or more is less than 0.05. So a couple things with that. First of all, when we talk about successes and trials, here we're just looking at what it is that we're trying to get. Okay, and this language comes from the probabilities, origins in dealing with gambling games and games of chance, things like that. So you could be betting on, let's say that you're betting on having girl children or something. And so we might refer to that as a success outcome. Even in, as we'll see, especially later in the course, if we have stuff that is really negative, we might look at, somebody catching a disease as counting that as a success outcome, even though in a realistic sense, that doesn't make any sense. It's just because we're looking at counting up the number of occurrences of whatever thing it is that we're interested in. And we call that a success, whatever we're counting. And it could be something that in real life is actually really negative. Okay, like somebody catching a disease. So here, and a trial is not like we're rolling a die or tossing a coin. It's having groups of 8 babies, right? So that's one trial here, and then X girls would be, for example, X girls would be our successes. Okay, that's half of it. The other half is you want to be careful about all the highs and lows. So it says significantly high number if the probability of X or more successes is 0.05 or less. 0.05 or less means that there's a low probability. There's a 5% or less chance of getting X or more successes. Okay, we want to contrast this with the other end, a significantly low number of successes. And the wording here is really similar, except that it's a significantly low number of successes if the probability of getting X or fewer successes is 0.05 or less. So again, X is significantly low if the probability of X or fewer is 0.05 or less. Okay, so a way to kind of maybe simplify that is as follows. Significantly high would mean that X or more happens rarely. Significantly low would mean that X or fewer happens rarely. I substituted the phrase happens rarely in here just to take some of the numbers and a little of the wording out. By happens rarely, we're going to take that to mean has probability of less than 0.05, something that just doesn't happen very much. Something significantly high if you get that many or more occurrences, not very often. That's significant if it doesn't happen very often. Significantly low if you get X or fewer, rarely. Okay, that's the criterion for significantly low. Okay, so let's try it in the context of our example here. We want to find the probability of getting exactly 7 girls in 8 births. So 7 girls in 8 births is 0.031. Okay, right there from the table. Doing it this way has the advantage that there's a lot less calculation. Okay, find the probability of getting 7 or more girls in 8 births. That's 0.031 plus 0.004, and that's 0.035. Okay, the probability of getting 7 or 8 girls. Okay, is getting 7 girls in 8 births significant? Yes, the probability is less than 0.05. Okay, the probability of getting 7 or more girls is less than 0.05, less than a 5% chance. So yes, that's a significantly high number of girls. Okay, is getting 6 girls significantly high? Okay, so getting 6 girls, that will be 0.109 plus 0.031 plus 0.004, and that is more than 0.05. So no, it isn't. Okay, because it doesn't happen that rarely. The chance of getting 6 or more girls is about 15% chance. And we've determined, or our criteria for significantly high or significantly low is that the probability has to be less than 5% chance. Okay, we could say the chance of getting 1 girl is significantly low because 1 or 0 has a probability of less than 0.05. In fact, let's go ahead and add that. So is 1 girl significantly low? Okay, So the probability of getting no girls is 0.004. One girl, it's 0.031. 031 and 004. Let me do them in order. 004 and 031. Okay, the first one was probability of none. The second one was probability of 1. Okay, and so that's 0.035, which is again going to be less than 0.05. So yes. All right, so that's significantly low according to the criterion there about the probability being less than 0.05. All right, so we're almost there, okay? The natural question that comes next is, why is it that I'm using both of those? Why is it that for one girl, I'm not saying just the 0.031? Why do I have it 1 and 0? And then for this one, we wanted to know the probability of getting, is 7 in 8 girls, is that significant? I didn't just use the 0.031. We used 0.035, which is both the 7 and 8. So is that significant? We needed the probability for both outcomes for both 7 and 8. And so let me address that. Of course, if you're fine with it, then you're fine. But if not, then we need to address that. So why isn't it exactly? Why was it X or more successes for significantly high, or X or fewer successes for significantly low? Okay, so a little bit more tangible or familiar example of that to illustrate. Let's say that you're taking a class of some sort, and these are the test scores that come out. And there's 20 test scores here, and we want to know how good this 80 is relative to these other scores. So if we just wanted to consider that 80, the 80 here, the probability of getting that 80 is 1/20th, right? Because there's 20 scores here and one of them is an 80. So does that really convey that that's significantly high or not? In a way, not really, because the probability of getting an 81 or an 82 is the same, right? They're both also 1/20th or 5% chance. In fact, a 72 has the exact same probability. You want to think about, how do you decide if your score is high or not relative to others, not in an absolute sense. What would tell you that the 80 was high if there were relatively few numbers bigger than it, right? Let's say that you scored an 80, just as shown here. Okay, you didn't do too bad. But then let's say that the only other scores higher than you were an 81 and 82. Okay, now it seems like you've done a lot better. Why? Because the number of scores higher than you, well, there's fewer of them, fewer scores higher than you, but you do need to take into account the ones that are at the higher end. What is the probability of getting a score 80 or higher? Okay, now it's much less than here. But you do need to take into account the values that are higher than the one that you're looking at. Similarly, if you wanted to know what is the probability of getting a, is 63 significantly low? Well, it's significantly low if there's not that many scores at that level or below. Okay, and so you do have to take into account how many values there are below that point, not just what those specific values are. So yet again, another example, 65 right here, is that significantly low? Well, there's only a 5% chance of getting 65, but getting a value 65 or lower, there's 1, 2, 3, 4, 5, 6 out of 20, which is a 30% chance of getting a value 65 or lower. Okay, so that takes us basically to the end of section 5.1. We looked at what a probability distribution is. How do you decide if this table that you've got, is it a probability distribution or isn't it? And we looked at some formulas for mean and variance and standard deviation for a probability distribution. And we looked at 2 ways to decide whether values were significantly high or significantly low. One was in terms of, are you more or less than 2 standard deviations from the mean? And then the other one was in terms of the probability of getting a result is at least as extreme as the one that you're considering, either on the high side or low side. Okay, so that takes us through all the basics, if we can call them that, all the basics of probability distributions. In the next sections, we'll go on to 2 specific kinds of probability distributions. In the meantime, though, let me know if you have any questions, and then have a great day.